Hey, welcome back. This is another exciting episode of Mr. Takeda Teaches Algebra. I'm your host, Mr. Takeda, and I'm going to teach some algebra right now. This is lesson 8.5, Using the Intercept Form, part 1. Yeah, when they wrote this part of the book, they put a lot into this one lesson, so I have to split it up. Otherwise, we'll be here forever. The essential question, what are some of the characteristics of the graph of f of x equals a times x minus p times x minus q? Okay, so this thing here is called the intercept form. Why is that? Well, it's because we can look at these things and get the x-intercepts of our parabola. Here we go. So quite easily, you know that if x minus p equals 0, then x equals p, right? So it's kind of like the opposite of negative p, the opposite of negative q. So we've done plenty of those things using the zero product property before, and that's all this is here. But in this case, we're going to plot them on a graph, and those are our x-intercepts, p and q, here and here. The axis of symmetry is halfway between p and q. So to calculate it, you add p and q together, and you divide by 2, and we get this line of symmetry, our axis of symmetry. Okay, so that's going to give us kind of the center line of the graph, and the graph, of course, opens up when a is greater than 0, and when a is greater than 0, we consider that positive, so we're smiling. And then if a is less than 0, that leading coefficient's a negative, then we're frowning, right? It's a negative. Oh, I'm sad. Okay. So, and also you can use this axis of symmetry to calculate the vertex if you want to sketch this out. And that's what we're going to do. So the first thing here is we want to graph x minus 1, let's say this one more time, negative 1 times x plus 1 times x minus 5, then describe the domain and range. Well, I can see that my x-intercepts are going to be negative 1 and positive 5. So negative 1 and positive 5. Okay, so I can kind of see here that 1, 2, 3, 4, 5, 6. I'm halfway between. I've got 6 spaces in between. So 1, 2, 3. My axis of symmetry is going to be here at 2. But how do we calculate that axis of symmetry if we had a fraction or something? Negative 1 plus 5 over 2. So that's 4 over 2, which is 2. So that's x equals. And that's my axis of symmetry is at 2. I'm going to use one of these neat kind of nice line drawing tools here to kind of put that in. For me, it would be a little bit neater. That's not what I want. Not at all. I want a line. Sorry about that. Okay. Now we find the vertex. Since I know my x value, I can say f of 2 is equal to negative 2 plus 1 times 2 minus 5. So that's going to be the opposite of 3 times negative 3. So 3 times negative 3 is negative 9. So the opposite of negative 9 is 9. So my vertex is going to be at 2, 9. So my other point is up here. There. And if we wanted to make this a little more complete, I could calculate a y-intercept, and of course the y-intercept is the value of y when x equals 0. So that would be negative 0 plus 1 times 0 minus 5. So basically it's 1 times negative 5, which is negative 5. So the opposite of negative 5 is positive 5. So I have another point right here. And then I know symmetrically, if there's 2, the distance is 2 to the line of symmetry on the left, then there's another point 2 to the right of the line of symmetry. So I've got 5 points here on which to graph. I'm going to sketch those in now, but you can't. There you go. That might have taken me many tries, and that might have been able to do it on the first try. You'll never know. But yeah, there's my vertex, my y-intercept, and it's kind of like it's reflection or whatever you want to call it. It's corresponding point, and then my 2 x-intercepts. That gives me enough to kind of sketch in a nice parabola. Okay. We're going to graph this quadratic function. Now, this one is not in, oh, before I forget, of course, the domain here is all real numbers, and the range here is going to be y is less than or equal to 9, because my range is anything below my vertex. Let's go back. Okay, 2x squared minus 8. So what I have to do here is put this into that intercept form. Okay, so I'm going to have to factor this. I'll factor out a common 2, that leaves x squared minus 4. And then that becomes x plus 2, x minus 2. Okay, so real easy. My x-intercepts are at negative 2 and positive 2. Negative 2 and positive 2. My line of symmetry is right here on the x-axis. It's not a negative number out here, so this should be a positive parabola. It should look like this. When I'm done, I want to calculate my vertex. My vertex is f of 0. So f of 0 equals 2 times 0 squared minus 8. And so that's f0 squared is 0. 0 times 2 is 0. 0 plus negative 8 is negative 8. So down here. And that's it. I've only got a few points here. I could, if I wanted to get some more points, I could do like f of 1. F of 1 might be nice. So f of 1 equals 2 times 1 squared minus 8. And 1 squared is 1. 1 times 2 is 2. 2 minus 8 is negative 6. So that would be here and here. Okay, so sketching that in looks like this. Ta-da, something like that. Domain, again, all real numbers, and range is y is greater than or equal to negative 8. And if we go back and look at the original in this form, what I like about this form is I can look at this number and know that's my y-intercept. Okay, if it's in this intercept form, we can't see that. I'd have to plug 0 into all these and get 2 times negative 2 and get negative 8 that way. But in this form, I can see that y-intercept. Okay, what's next? Using intercept form to find the zeros of functions. You already know how to do this. This is solving using the zero product property. But the only reason this example is here is to introduce you to this idea of zeros of functions. And again, that is just x-intercept, which we've done. So in this case, x minus 1 is 0, then x equals 0. And over here, x equals negative 2. So I don't want to spend too much time on that one. That's pretty straightforward. But again, So the purpose of this is to have you use the word zeros of the function and know that means x-intercept. Okay. Factors in zero for any factor x minus n of a polynomial. Okay, so a binomial factor of a polynomial. N is a zero of the function defined by the polynomial. What does that mean? All this is really talking about is that zero product property again. So we factor it down into a binomial, we set it equal to zero, and then we know, again, it's like the opposite with negative n. If x minus n equals zero, then x equals n. That's our zero. Like it says, n is a zero. Again, use that. Think about what that vocabulary means. We just introduced it to you. Okay, so here's a couple examples, and we've done these before. We're just solving. We set it equal to zero, and then we factor and solve. Okay, so over here, I'm going to factor out a negative 2. That leaves me x squared plus 5x plus 3, 4, 6, I'm sorry. I'm sorry, yeah. 6. So when I factor this out, these are these binomial factors we were just looking at. We've been doing these already. X plus 3 and x plus 2. So the zeros here are x equals negative 3 and x equals negative 2. Same exact thing we did before, except now we're just calling them zeros, not solutions. Over here, this is kind of factored for us already. I've got x minus 1. Then I have a difference of 2 squares here, x squared minus 16, which would become x plus 4 and x minus 4. So my zeros here would be x is negative 1, negative 4. I'm sorry, this is positive 1. Positive 1, negative 4, and positive 4. It's kind of like the opposite of those numbers you see in there. And those are things that we've already been working on. And that's it for part 1. Like I said, I split this up and I'm still coming up to 13 minutes here. Thanks a lot. Have a great rest of your day.